Hi everybody, this is lesson 5.4, Compounding Interest Makes Sense. So in this lesson we'll go and step away from linear model and look at other situations that can arise in applications. So let's read the specific objectives. Students will understand that compounding is repeated multiplication by compounding factor. Compounding is best expressed in terms of exponential growth using exponential notation. Exponential growth model is the compounding of interest on an initial investment. Students will be able to calculate the earnings on principal investment with annual compound interest, write a formula for annual compound interest, and compare and contrast linear and exponential models. So the objectives already kind of imply of what kind of model we're going to be looking at. So let's go ahead and just explore it from a given situation, and then we'll outline the properties of this new model. Problem situation number 1, the 5-year CD. Suppose you invest $1,000 in a certificate of a deposit called a CD with a 5-year term that pays a 2% annual percentage rate, APR, and the compounding period is 1 year. So a CD is basically a savings account that gives you a percentage added to your account at the end of the term. The terms can be, we have a term which is 5 year altogether, and then you also have how often you will be getting money. So let's just understand what's going on here in this situation, and then we'll be able to illustrate the model more concrete. All right, so you start with something that's called a principal, which is $1,000. All right, and you will be getting a rate of 2% APR yearly. It's a yearly rate. And then you have this term, which we'll explore a little more as the lesson progresses, called the compounding period. Okay, so let's go ahead and see what's happening here. I'm just noticing right here that it says 2% and then later it changes to 3%. So we got to be consistent. So let's just not confuse ourselves. I already wrote 2%, so let's keep it as 2%. All right, and let's go ahead and try to explore it. Okay, so let's do the calculation. So we started with $1,000 and we add 2%. I'll give you a moment to do the calculation, and I'm strongly encouraging you to use a one-step thing that we've learned in lesson 1.2 or 1.3, somewhere at the beginning of the semester. I have emphasized that continuously throughout the lesson, so I'm really hoping you still remember it. I'll give you a moment. All right, so now, if you've done the calculation by taking $1,000, multiplying it by 2%, like that, getting what is it, $20, and then adding 1,000 to 20. That's all right, but really, I mean, we went through the whole semester of these lessons dealing with the percent all the time, so really hoping that we understand that if we add 2%, you just multiply by 1.02. 100% and a 2% give you a factor of 1.02. Okay, you get the same answer. All right, so now the feature of this account is that the second year that you start, you don't start with $1,000, but you are starting with 1,020. You see, that's the idea of compounding, is that you are getting you're starting with the higher amount. So now if you are getting another 2%, that 2% is added on to a balance of $1,020. Okay, so go ahead and do the calculation. I'll give you a moment. Again, do it in one step. All right, so you're multiplying it by 1.02 again, and you're getting an answer is, let's round it to the nearest cent. So it's 1,040.40 cents. You see, you're not getting 1,020, you're getting 1,040, an additional 40 cents because you have started with the larger amount. Okay, All right, let's continue. So we're getting 1,040 now and 40 cents. And you're multiplying it by 1.02 again. So it's already in my calculator, so I'm just pressing the button again. So I'm getting that $61.21. At that point, I have to round. All right, I'm multiplying it again. So whatever I had from before, I'm just going to go ahead and write it like this. I'm multiplying it by 1.02. I'm getting $1,082.43. I press the button again on my calculator, and I get $1,004.08. All right, I'm gonna put that in a box. So that is the ending value. All right, so now I want you to think critically of what has happened. We started with $1,000. I'll put it on top, and we did this at every step. Okay. So if that pattern continues, all right, can you describe this pattern mathematically? All right, like for instance, let's say this was going for 10 years. All right, it will be annoying to keep multiplying it by 1.02 so many times. So what could be done? So if I start with $1,000 and I go for 10 years, I'm multiplying by 1.02 10 times. What should I put here? What mathematical operation could I use to make this computation quicker? We actually done this a very first lesson when we talk about number of children living in poverty. We did this the first lesson, and we're talking about the doubling idea. So you remember what happens? What do we use? Yes, we use an exponent. So if I want to go for 10 years, I'll do just that. Alrighty, I pulled up a calculator right here, the decimal scientific calculator, just to emphasize how you put the values in. Alright, so when you use this, I can recommend that you use decimal scientific calculator for your calculation, or use a scientific calculator that you could see what you enter, not an iPhone, because that way it would be more precise. Not precise, but you're more confident that you're entering the values correctly. Like you see here, I'm using an exponent button, and I see exactly what I entered, and it gives me a reliable answer. You see, I'm not multiplying it by 10, by the way. I'm using that as an exponent. So multiplying it like this, 1.02 times 10 times, that gives me what we call a growth factor. So that thing right here, each year, that's called a growth factor. So if you continuously applying it, then you can use exponent to describe this. So you get $1,218.99. It's just another example. It doesn't need to be 10. It can be 15. It can be whatever. Whatever something happens on a repeating basis, you can stick an exponent right there. So what would it be after 2 years? Well, it's $1,000 multiplied by 1.02 T years in a row. And that becomes a mathematical model. So here we go. And this is A. Usually we use the A for the amount. Are we asked to write it? It's coming up. Yes, so one thing that I would like for you to see, looking at the progression of your balance 5 years in a row, is the model linear? What does it need to be true so to say that the model is linear? So that model is definitely not linear because it does not have a constant rate of change. Check this out and remember this very clearly. The reason why it's not linear, because as you go here, this difference is not the same. Check this out. At first, it's $20.40. The very first year, it's $20. Then the following year is $21 and change. Well, I'll subtract it just to give you correct numbers. So it's $61.21 minus $40.40. So that's $20.81. And so on. So I'm not going to spend now time and keep subtracting, what I want you to show is that the difference is not the same. Okay, so the difference is not constant, and that's a characteristic of a linear model. There is something that's constant. It's called, there's a constant ratio. Okay, however, there is a constant ratio of 1.02, which is called a constant growth factor. Growth factor. That means we're multiplying by the same number over and over again. And when we have such a property, we have a constant rate of growth, we call such model an exponential. In this class, we're going to be dealing with only two models, linear and exponential. So this is the first lesson on exponential model. Alrighty, so that model is exponential. Now we can apply this, and just to make this a little bit more efficient, I don't want to spend a lot of time graphing this, but I do want you to see how the model is going to look like. So first, what I would like for you to do is to do the calculations for using that model for this. So can you fill out this table? And then what you will see in a minute, well, in a few seconds, where you'll see the entire table filled out. And then we're going to go ahead and use Excel to graph this, okay? Alrighty, so I'm just gonna enter 1 for you. So for example, for 10 years, we already did this, so we just copy it. So it was 1,000 times 1.02 to the power of 10, and we got the answer of 1899. All right, now CD doesn't go usually for more than 10 years, but for the purposes of understanding of how the money is going to grow and how it will then look visually, we're going to go ahead and just continue using this pattern for all these number of years, just to see what's the effect of this compounding, where you keep adding 2% for a longer period of time. All right, so I'll give you a moment to fill out this entire table. Go ahead and use Desmos Scientific Calculator to do so. Alrighty, so let's review. So what I did is that I put all of those values in the Excel, alrighty, and it starts off with $1,000. I think you know what, I'm going to just go down just one value so we can kind of go to 0, alright, like this. Alright, so we start with $1,000 and then it grows all the way to $10,000 over the course of period of time. Now, we notice that the graph is not linear just because the difference between these is not constant. Now, that means if we graph this, we shouldn't expect to see a line. But the graph of the exponential model, you should also recognize. So what I'm going to do, I'm going to insert a graph right here. And I want you to see right here that this is not linear, okay? It gives you the shape, which is a curve. It's a curve, and we call such shape exponential. Notice that it starts off at $10,000, and then it has the shape where it's curving up. All right, and the further you go, the higher it's going to curve up. So my point is when you encounter a model that's not linear, you do not expect to see a linear graph. An exponential graph has that particular shape. Okay, I can go ahead and maybe copy this into our into the notes right here. All right, let's see if I can even put this right here. Oh, excellent. All right, so here it goes. The only thing I'm going to do is I'm going to label it properly, right? So this axis right here is the time. It's in years. And then this one axis right here is the amount at any given time. All right, so now it's asking us to choose a formula that will describe a general CD where the compounding happens every year. In this course, we don't describe any other type of compounding. So can you go ahead and write this formula using the letters there? A for the amount, P for the principal, which is the initial amount, R is the rate, and T is the number of years. So you'll see a couple of choices for you to pick. So go ahead and based on what we discussed, can you write a general model? Okay, so the general model is going to look like this. You have the amount at any time equals to the principal, the amount that we start off. And then you do have an exponent. And then the question is, well, if the R is the rate, let's say a percentage, right? We convert that into a decimal. We don't put that in here though, right? Because if you just put it in here, it's going to be 0.02 to the power of t. Where's the 1? And for the, again, from the beginning of the semester, when we talk about the percentages, if you want to go up to do a percent increase, you do 1 plus whatever the rate is. So I'm reminding you this again. It also works when we are writing the formulas. So that would be the correct model. 1 plus the rate. What is 1? 1 is the starting, right? It's 100%, and then you add an additional percentage. Okay, so that's a general form for the growth. So this is a growth relationship. It's an exponential growth. It doesn't only apply to finance, it applies in the other situation. Next lesson, we actually will see that. All right, let's talk about the depreciation. It's losing value. So this is the opposite of accruing interest when an amount of money is invested. So it's opposite. So we know the cars lose their values every year. Maybe not during 2021 when the value of the used cars have been spiking up, but during a regular, during normal times, I guess the things depreciate. And cars is an example. So let's look at the car that is worth $26,000 at the start. And let's assume that it depreciates 50% each year. So it's losing 15% each year. Can we do the calculation of how much this car will worth each year? So let me give you a moment to do the calculation for the first year. So take $26,000 and deduct 15% of its value and do the calculation. I'll give you a moment. So once again, guys, if you did this by taking 15% of 26,000 by multiplying 26,000 times 0.015 like this, 0.15. All right, so what is this equal to? So 26 multiplied by 0.15 gives me 3,900. And then you take 26,000 and then you subtract 3,900. That's fine. You understand what percentages mean. Excellent job. But we need to do better than this in this class. The reason is because we've learned this idea all the way at the beginning of the semester. If something goes down by 1%, you can use factors instead of doing it in 2 steps. Go all the way to the beginning of this course when we did this. I think a very second lesson or the third, somewhere around there. I think it was lesson 1.3. So to do this depreciation in a more, I would say mathematically mature way is to do this. If there is a 15% depreciation, that means the car after 1 year is going to worth 85% of its initial value. Okay, so to calculate that, we're going to do 85% multiplied by the value of the car, and you can double check that will end up equal to $22,100. Why does that matter? Well, because then you can actually make that same step ahead, because there's the same depreciation factor that we expect. So we're going to go ahead and do the same thing again here by multiplying it by 85%. Okay, so you take $22,100 from before, and we're going to multiply it by 85% to get the next value. So let me do that. Multiply by 85%. So the car is now valued at $18,785 if we assume the same 15% depreciation. Now you see, now you want to go 5 years in a row. So yeah, you can go ahead and do it, the calculation these many times. go again, third year, fourth year, fifth year. But I want you to think more critically. If we start with $26,000, right, and we do 15% depreciation year after year after year, all right, I can write it over here. Then how can we start with 26,000 and do 5-year depreciation by 15% 5 years in a row? And it's not going to be 15% times 5. No, it's not working like that, because at each year your value is actually becoming smaller. So it's not the same 15%. So it's not going to go down by $3,900 every year. No, because the value is smaller. Okay, the next time you do 15%, it's going to be less than $3,900. So you need to think of this as depreciation, the constant depreciation. So how do we do this? I'll give you a moment. What would it be? All right, so what you do is you include an exponent. An exponent, so you say times 0.85, 5 years in a row. 0.85, 0.85, 0.85, 0.85, 0.85, and that gives you the total depreciation. Now, if you're wondering, by the way, 0.85, let me show you this. 0.85 to the power of 5 equals to 44%. You know what that means? That means in 5 years, your car is going to worth 44% of the value that it was before. So it means it's going to lose more than half of its value. You see? But what if you do 15 times 5 like that? That shows you that it's going to lose 75%. But it doesn't lose 75%. It's actually losing about 65%. Oh, not 65, 55% of its value. So there's a very different thinking. It's not a linear model. So actually every year it loses a little less money, because it's valued at the less each year. Okay, so you'll use the exponents, so we can go ahead and fill this out. So I'm going to go ahead and use Desmos to do this calculation. So 26,000, and again, I'm encouraging you to use Desmos as well, or calculator, that you could see exactly what you enter. All right, so I'm confident in what I'm getting. So it's $11,536. All right, so using the same thing, go ahead and fill out the rest, and I will again transfer it all in Excel. Go ahead. Here are the numbers, right? 8, 10, and 12. So let's do the same calculation. By the way, you do start with 26,000, because the assumption is you begin and then you go year after year after year. Alrighty, so here's I transfer thing into Excel. If you're wondering what I did, is I basically, see if I double click here, so I put $26,000 and I multiply by 0.85 to the power, and then for the time I just used that cell. Okay, and then what I did is I just double tap at the little square. 1 second, I have to do escape so it doesn't disappear. Alright, and then I just double tap right here, and it fills me out the entire table. Notice the table in the lesson just asks you to go after 12 years, but I went to the 15. I want you to just see that the difference between these two numbers is not constant. Let me actually put that right here. So if I do the difference, if I go ahead and compute the difference between those two numbers, let me go from here. So if I take, let's say, the difference between this, and then I subtract, so I do minus that, okay, and then I double tap. You see this in parentheses? That means that it's decreasing. So at first the value decreases by $3,900, then $3,300. It depreciates slowly. Okay, so it doesn't lose as much money. Okay, and that's kind of realistic situation because the car is not worth as much every year. So if it loses the same 15%, that 15% is smaller. You know, year after year after year. What I'm describing here and emphasizing is that the model right here is not linear. So to be linear, the difference needs to be constant. So when you're writing these exponential models, you don't get a constant rate of change. And if we graph this, we are not going to see a line. So when I'm putting this here, when I'm asking Excel to graph this, I'm getting this. You see, I get this depreciation where it starts off at 26,000 and then it's not linear. It's curvy. It's curvy like that. Okay. So that would be the graph. Let me go ahead and maybe copy that into the lesson as well. Okay. Here we go. Let me paste this. All right. So this one gives us the time, and this gives us the value of the car. I think they use letter D for that. Okay. Oh, we actually have nothing else to do in this lesson. I do want to maybe emphasize just one thing. I'm not sure why it's not written right here, but I do want to go ahead and just write like a general model. So the general model right here, oh, it is asking it right here. So the general model would be D, the value of the car, is going to be what? I'll give you a moment to write it. So if it starts with $26,000 and depreciated by 15%. So it would be $26,000, all right, times 0.85 to the power of T. Okay, and in general, if you want to do the depreciation model, if you have D as being the amount that the car or whatever worth, and then you got R is the yearly rate, and T is the time in years, then you get D equals to, you can say, oh, that's initial value. Maybe let's say I as being the initial value. You can say, okay, it's the initial value, and then it is T, again the R, but instead of 1 plus, it's going to be 1 minus the rate. So that's a depreciation model, and 1 plus is depreciation. So not too bad. What's nice, it's actually, we are bringing this back to the the second lesson in the curriculum when we talk about percent. We're bringing it again. We're just tying it together in the form of a model. The characteristic of a model is that there's a verbal description, there is a table that you can make, there's an equation you can write, and there's a graph that you can make. Okay, and that's exactly what we're practicing in here. All right. The next lesson will also deal with the mathematical modeling, and on that, we're going to finish this lesson.